Welcome, everybody, to another episode on dynamic programming. Today, we are trying to tackle DPV 6.4 corrupted document. I have remade this video because of the missing details and the quality of the video, which was the original one done before. So, hopefully, this is clearer. And if you have any more questions after this, do leave them in the feedback. And with that, let's jump into the problem. So the problem is that we are given a string um, S, which has a bunch of characters, let's say 1 to n. The string has been corrupted, so there is a loss of punctuations. For example, if this sentence is "you are a bold one" and it has spaces and punctuation, etc., which basically are separating the words in the sentence. If these punctuations are have disappeared, let's say there's no spaces, no commas to separate the words, then it becomes "you're a bold one" like that. And you are now to reverse this process. So how do we reverse the process? We are given a dictionary in which you can look up a word, and the dictionary will return you whether it's true for valid words and false for invalid words. So the problem statement then becomes that given dynamic programming solution, give a dynamic programming solution that determines if the whole string, which is this whole string, is a valid sequence of words. If yes, then you should output the sequence. Now, the first part is supposed to be done in order n square time, which is give a dynamic programming solution that determines if the string is a valid sequence of words. That has to be done in order n squared, and then it says output the sequence. So with that, let's look into a recurrence or a way to solve this so that we can work um, through all possible situations. So we will define this vi function, and this function will output 1 or 0 depending on the following. First of all, vi is the final solution, which is saying whether, which is what is being asked in the question, is if at position I there is a sentence preceding this point, right? So it's giving a 1 or 0 or true or false based on the fact that if there is a valid sentence all the way from the beginning to this ith character, then we call it a 1, saying there is a valid sentence here. If it results in a false, that means that the ith position from the beginning of the sentence to the ith position is not a valid sentence or a sequence of words. And keep in mind that here the words don't really have to mean anything. They just have to be part of dictionary, right? Semantically, it may not be a valid sentence, but just as long as it is a sentence, which is a collection of words, as long as, so the only objective here is to figure out if this is, syntactically uh, a sentence. It may not mean anything, right? So that becomes yet another thing, maybe a second problem could be built on. Um, then the recursion that we're talking about looks like the following. So at any given location I, let's say we are trying to figure out the ith position in the sentence, which is we are looking at a string of characters from 1 to I. So then we will take another variable j, which is going to scan from 1 to I, right? It'll take all possible values from 1 to I. And at that point, we will break the previous sentence, and from j to I becomes it becomes a word, right? So we can, by scanning j, we can get words of all the length, all possible lengths ending at I. The key is that the word that we are talking about always ends at I, and it's of all possible lengths from the beginning of the sentence to one less, then one less, one less, and so on and so forth till it becomes a single character. So that is the key. Once you understand this part, that this dict I, j comma I, is a variable sized word, and we're going to scan all possible words ending at I. As long as there is a valid word such that just before this word there was a sentence, there was a valid sentence, so a combination of the previous sentence plus this word, as long as both these conditions are true, right? This word has to be a valid word in the dictionary, and the sentence just before this word has to be also valid. As long as both these conditions are true, we have um, a true at the ith position. Now, when we go down this example, you will see that multiple values are possible, right? At any given point, there could be multiple words. At any given I, there could be multiple words ending at that position, which can lead to more possibilities than just one, but we'll cover that later. But at this point, we just want to cover the fact that the condition, when you think about the ith position, you should think of words of any length ending at the ith position. And then if one of these becomes a hit in the dictionary, which is true in the dictionary, then there must be a sentence before it, which is also valid. Okay, so now let's work out our example, right? You are a bold one, which is what we thought our sentence was. Once the punctuations are removed, it looks just like you're a bold one and it's just a bunch of characters. How can our program or software decipher that there was that statement behind this? Given the dictionary, how do we do this? So I've written down this algorithm here. This is the algorithm that we had used. So what we're going to do is there are 14 characters here. Obviously, there are no punctuations. So I wrote down 14 from I is equal to 1 to 14. And like I said, inside this I loop, there is also going to be a J loop. So we're going to, for every character, we're going to see words ending at that position, but of various lengths. And keep in mind that half of this matrix is going to be empty because, uh, when you're looking at I, the words cannot be of size more than one. So it's only going to be at the most one character. So given this, we're going to store two things. One is whether it's true or false or one or zero, whether this was possible, a sentence ending at I equals one. Was this a sentence? This first one says that whether there was a possible sentence. The second one indicates the previous location. If this is valid, then there must be a previous sentence, right? And if a sentence ends at this location, then there must be, if you remove the last word, then the previous sentence ended at some position. So you will capture that previous position here, right? So for y is not a valid word in the dictionary. So it's going to be a zero here. The first location is going to be zero. And the second is really meaningful. It is meaningless because when this is zero, that means, there is no previous sentence. It's really, you should ignore this. So the second one is ignored. And we'll see shortly that there are conditions where this is one and this becomes meaningful, right? But when the first one is zero, the second position, you could just, it's meaningless. So you could ignore it. Could be X, doesn't matter. So that's basically capturing all this here, right? It's really applying this algorithm. When I equals one, there's j can only be one value, and we take that. And when you're going from one to one, you only pick up the alphabet y. When you pick up the alphabet y, the v of I basically becomes a zero uh, because v of 1 comma 1, when you do the 1 comma 1 here, you will find that's only y, right? So the dict part fails. The prev part is okay because um, we assume that the prev of 0, right, prev of 0 is a 1, which means that just before this sentence started, um, this v of 0 was a 1, right? So that's very important to understand that the initial condition here is that the prev, sorry, not the prev, but the v of 0 is a 1. V of 0 is a 1 is the boundary condition here, right? Because before this sentence started, it was always possible to make the sentence at that 0th position. So, for example, I mean, this could have started with, let's say, instead of y, it could have started with the a, right? When you put a, and if you had run the same algorithm, you would have, at least this word would have hit the dictionary. So dict of this would have been, see, this dict part would have been true. And if the v of 0 would have been, v of 0 is true because that's a boundary condition. So would have given us a 1 here, right? 1 and 0. That would have come out to be But in this case, Y is not in the dictionary, and so you're not going to see that. So it becomes 0, 0. Next, we move on to the second character. When you look at the second character, what happens? You have two possibilities. The J is going to scan from 1 to 2, right? And when you do 1, you get YO in the dictionary. And when you do 2 to 2, you just get O in the dictionary. Both of those not going to give you anything. So this is going to be a false and false. And like I said, the second value is meaningless in this case because the first value has to be a 1 for the second to mean anything. So you're just going to write this, and then we're going to move on to the next one. And the next one, when you get to the third position, which is YOU, YOU, you can see that the very first one, when J equals 1, gives you YOU, the second gives OU, and the third gives U. These are all not going to work, but the first one works because it's part of the dictionary, and V0 is a 1 because that was our initial condition. And if V0 was 1 and dict of 1, 2, 3, see this condition now becomes true here. So this becomes true. So now, like I said earlier, when this is 1, when the first position is a 1, you must remember where you came from, and this is meaningful. If this is 0, this doesn't matter. If this is 0, this doesn't really matter. You don't even have to compute it, just write, anything, just random number there, 0 there. It doesn't even matter. Previous is only meaningful if this was a word, right? If this was a word. So in this case, it is a word because it's YOU. YOU gets a dictionary hit. And so the J minus 1 here, because the J is 1 here, so J minus 1 becomes 0. So V0, and 0 is where we came from. So 0 is recorded here, right? Okay. So moving, excuse me, moving on from there, when we get to 4, I equals 4, J is going to go 1, 2, 3, 4. And when J goes 1, 2, 3, 4, you can try the same thing. When J is 1, you get YOUA, then you get OUA, UA, and A. Now, A is a valid word in the dictionary. And if you do the valid word in the dictionary, then the previous one becomes V3. And we know that V3 was 1 because V3 had at least a valid uh, possibility. So V3 becomes 1. And let's stop there for a moment. So what is V3? Now the way V3 is computed is that because V3 has all these possibilities, but V3 is true if any of these values becomes a 1, which is, in this at V3, we saw that the first, when J equals 1, this was a 1. So you can write V3 as 1. Basically, it's if any of these values is a 1, then you write this as 1. If all of these are red, then you write a 0 here. If all of these are red, you write a 0 here. So that's how you compute V3 here in this case. So when you're looking at V4, you know that when J was 4, you got an A here. An A hit a dictionary here. But when you did dict of A is true, you would check V of 3 here, right? V of 3. And V of 3 we know is a 1 because at least one of these was valid. So V of 3 was 1. And therefore, this would give you a hit. And this gives you a hit, so it becomes 1 because it's true, and the previous came from 3. The previous sentence ended at 3. Because that's by searching here, we found that there was a valid position, and that was 3, right? The word of size 1 was the matching one. So here's how you got to you are a. And then you move on to the next one. You apply that, you find there's nothing matching here. And then you find you are. So R has now been found, right? And see that we scan through everything, and you can see that none of these are valid words, so this would fail the dictionary test. The only one that passes the dictionary test says that the previous one would have ended at 3, and so the ended at 3 would have been a U, and this would be an R. So here, all you have to do, don't worry about the previous stuff. All you have to do is record this, that at position 4, it's a true, so the first one is possible, and then the previous sentence ended at 3, right? Because in this condition, when J equals 4, the previous is 3. So that's how you find it. Now, keeping this on, and the next one is the interesting one. When you look at this A, when the next A comes in, you get two hits in the dictionary. One is area, because you see this, you are a, it becomes an area. So it becomes area or a. So at 7, 7, you get a hit, and now 4, 7, dict 4, 7, you get a hit, right? At 4, 7, the previous ended at 3. At 7, 7, the previous ended at 6. So you have to remember these. There's an overlapping word situation happening here, right? This is good to see. We can sort through this. It's not a problem. The algorithm will find this. Now, like I said earlier, for V7, V7 is going to be a one because there are two ones here. This one is a one, this one is a one. So V7 is going to be a one. As long as there is at least a single one, then it should be a one. So V7 is a one. Then we just work through the remaining after V7. I'm just jumping across this because I just keep repeating this. And at the end, you have filled this. So now, is our answer true or false? We look at V14, and V14 has at least a single one here, which means V14 is going to be a one, which means that at the position 14, you are a bold one. There is a sequence of words here. That's what our algorithm is telling us, that there will be a sequence of words because at least one hit was found here. So the answer is going to be yes here. And now we have completed our algorithm. Now let's just quickly surmise what the order of this algorithm was. Now at there's n columns, right? And for each column there's n rows. So and the computation was done for each of these squares here. So there were n squared um, columns inside this matrix, and half of these were not used, so it doesn't really matter because you're talking about order. Order is still n squared. So the amount of time it took for us to do this is in n squared. And therefore, we meet the criteria for the question. So that's part one of the problem. We have solved part one. We have found the solution in order n squared time, and we have figured out that whether there was a sentence or there was no sentence ending at a given position in a set of characters, right? The next thing is reconstruction. Reconstruction means not only have we said that there is a sentence here, we will have to write down what is the sequence of words. But there is no requirement here on whether this needs to be order n squared or not. So now keep in mind, multiple hits can be obtained in any given column, right? And we can see that here when we saw area and we saw there are multiple possibilities. And when you thread through them, there may be multiple possibilities across, right? And so that's the important part, that we have to run through all these possibilities and we have to thread them through our reconstruction algorithm. So the way the reconstruction algorithm works is that we start at the end, we start at the last column, and then we say sentence I equals sentence of prev. And remember, the second thing that we had stored was the prev, right? And the prev is the ending word or ending character of the previous, before, excluding the word that ended up in the last one. Excluding that word, what was the previous character position? So sentence at the prev of I and the word. So what you have to pop is, if this is green, this is telling you that there was a word here that started at 12, 13, 14, which was one here, right? 12, 13, 14. And so you pulled out this one, and then you said, okay, now give me the words of the sentence before this was sentence 11, which was the prev, right? So that, and so on and so on. So now let's just take this one step further. Now, when you get to 11, 11 has this 1 comma 7, which means it was true, and the previous started at 7. And the 7 would give you bold. So you write down bold 1, right? Bold 1. So far, so good. But now you still have to decipher what was sentence 7. And sentence 7 has two possibilities. Now look at this. Sentence 7 is very interesting because you had the area coming out here and you had an a coming out here. So you would basically decipher both possibilities. And now, now at this point, you would basically fork off into two possible things. Either you go to sentence 6 or you go to sentence 3, right? So, and when you go to sentence 6 path, right? When you go through sentence 6, 6 is going to just be extracting R, right? So it's going to extract R and then it's going to extract U. But when you go through let's just fall back. So if you go to sentence 3, you're just going to get a U, right? So the two statements that we have extracted are you are a bold one, and you area bold one, right? So we have therefore extracted two different sentences using the dynamic programming algorithm, and there could be more sentences that we could have extracted based on how the words were uh, given to us. We could have found many, many more uh, uh, sentences inside the same. So there could be a subsequent problem that asks the question that is there a valid sentence? Is there a meaningful sentence? Not just a meaningless but a valid sentence. So there could be other rules, the meaning rules that could be parser rules that could be built on top of this, and that could be done in another video perhaps. But I hope that you guys understood and enjoyed this video, and hopefully this makes it clear how this algorithm steps through character by character, looking backwards at a word that could lie at any given position. And just by focusing on that word of different size that could have fallen at the ith position, we are able to walk backwards, and we are able to pursue that chain all the way to the beginning of the sentence. And then we can reconstruct it as well. So that's it for this episode, guys. Thanks for watching. And if you like this video, please hit like or subscribe to my channel if you love dynamic programming. Like I mentioned in my other videos, I have a full suite of DPV solutions which you can enjoy, or if they come in handy in your test preparation, etc. Um, you are welcome to use all this material for that purpose. And I hope that you come back here for more videos. Thanks a lot for your time. I'll see you in another video.